In this section, we're going to be discussing graph colorings. So the idea of colorings came from, I believe, just like coloring a basic map. So here's a very blurry map of the United States. And what we can notice from this map is that any two states that share a border are going to be colored with different colors, right? So visually that should make sense why we would want to do that, because if this state and this state were both colored in blue, it like even if there's like a black line between them, like it just visually gets kind of hard to tell that they are actually different states. But if you use different colors here, visually it's a lot more like distinctive. It's like very obvious, like, oh, this is California, that's different state from her. So anyway, the other thing that we notice is that even though this is like a pretty complicated map and there's kind of like a lot of states that are like sharing borders and stuff like that, we only need 4 colors to satisfy that condition of like no two like neighboring states share the same color. And so that's kind of surprising that like we only need 4 colors. Like you might think like, well, maybe there's 50 states, so like 4 colors seems like not a lot in order to accomplish that. And personally, I do think that's surprising. So anyway, one thing that we can do from this, so if we want to like study this question a little bit more, one thing that we can do is actually translate this into a graph theory problem, because turning things into graph theory problems, because a lot of things are kind of known about graphs, they tend to be like a little bit easier to kind of do mathematics on. So how can we turn this into a graph theory problem? Well, we do it as follows. We create a graph from this map where each state or region that you're concerned with is going to be assigned a vertex, and 2 vertices are going to be connected with an edge if and only if the 2 states are like neighboring, like they share like a border. Okay, so we'll draw an edge there, draw an edge there, edge here, here, here. Just gonna kind of keep doing this a little bit. There should be one right there. Here. Okay, actually want to make a point of this. So notice that there's like a little corner right here. Just because, so like if there's a corner, so this state and this state right here, they do touch at this corner. But if I were to color them both in blue, it wouldn't like really make this like visually harder to like tell what's going on here, right? And so like we don't actually draw an edge from this state to this state or this vertex to that vertex, if they like just touch at a single like corner. Like we only draw the edge if they are touching like at a like full line right there. So yeah, I might be missing some. I think that's good enough for now though. But yeah, anyway, so once we get that that graph, we can maybe copy and paste that, bring that over here. We can now turn this into a graph theory problem by now coloring the vertices. So maybe let's like make this guy blue, and then this guy can be red, this guy can be green. I'll use purple here, and I could just kind of do the same thing of say that 2, let's see, purple, I'm just gonna finish this, make that blue and make that green. Yeah, so I can do the same thing, make like a similar sort of condition where I say 2 vertices that share an edge have to be using different colors in the same way that two states that share a border have to have different colors. It's really like the same condition based off of like how we constructed the graph, saying that two states share a border or two vertices share an edge, therefore they have to be different colors, same sort of thing. Okay, so we can do this like with other regions as well. So let's look at these regions. So let's create a graph where we assign a vertex to each region. And we will draw an edge between corresponding vertices whenever they share a border. Okay, cool. And then what you can do, you could then, do this whole same thing of just like, okay, can we color each of the edges, each of the vertices, like in such a way that like, same sort of condition as before. If you're just trying to do this in terms of like, okay, can we color this, like just doing this by example, it's not really advantageous to like create the graph and then move the graph over and then try to color the graph. Like that's not really like gonna help you at all. Like you could literally just color them. So let's just color them right now. So so this one will be blue, this can be black, this will be red, this will be green. Let's make this green as well. This can be black and blue, and haven't used red in a while. And let's make this green. Okay, so we had to use 4 colors, but using 4 colors, we were able to do it. So you might wonder, like, okay, was there a way that we could have gotten away with doing only 3 colors in this one? So if I were to, okay, so definitely we have to use like 3 different colors here, here, and here. And then here, here, and here, we have to use 3 different colors. So maybe we're forced to use like a blue right here. And then say we have to make that one black at this point. And we have to make, okay, so we have, red, black, and then this has to be a different color. But at this point, this like can't be blue, it can't be red, and it can't be black. So at this point, like we actually do have to use a different color. So then from here, like you're forced to use 4 colors. So it looks like we need 4 colors over here. Okay, what about this one? So let's do blue, and then maybe red right here. And then let's make this one blue, and then I can make this top one green, and then this bottom one green. If I do this, then this one seems that we actually can color just using 3 colors instead, so that's nice. Okay, so some regions you can color with 4 colors, some maps, and then some maps you can color with 3. The big theorem is that any time that you have like one of these maps, you can color it using only 4 colors. Okay, so that is a theorem. So that's not technically what this theorem says. This theorem says that any planar graph is 4 colorable. So I claim that the 2 statements that I just said are really the same thing, but a planar graph is different from a map, right? So a map is not a graph, but like we can translate it into a graph. So let's go back here and like translate. Let's just, because this one's easier, let's translate this into a graph. Boop, 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 boop. And then we do that, that. Okay, so if I were to just kind of copy that over here, have something like this. Okay. So this is a graph for sure. What does it mean to be a planar graph? Well, it probably makes more sense to demonstrate something that is not planar. So this one is planar. Something that is not planar would be, or not planar like as drawn right here. Not planar would mean that two of the edges are like crossing over each other. So I'm kind of lying. Technically, I could like move this edge over here and all of a sudden now it actually is planar. But like as it was being drawn before, if I have like those edges that are crossing, it like would not be planar. You could do, let's see, the star one. Boop, 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 boop. The connected graph with like 5 vertices. This is like really messy. This is why I draw all the graphs like ahead of time for the slides. I'm not choosing to do it here. So this one right here, this like really messy one that I just drew, the one that you just have like the star and then like the pentagon on the outside. This one is like not planar at all. There's like a lot of crossings going on between edges here. You would have to like you could like take this one and you could like move it out here, and then take this one and then move that one out here. But then like you'd be stuck with, let's see, move those two out there. Anyway, I'm not gonna bother sort of justifying it, but like basically there's no way to like untangle this thing without like removing all of like the crossings between there. And the reason that we would like call this like, you know, this planar is because, you know, if they're not crossing each other, then it fits nicely on the page. If the two edges are crossing each other, then they're not fitting nicely on the page. Like if you were to like imagine that they are like two strings, one string is like lying on top of the other string and it's not lying like flat on the page. Okay, so if you have a map consisting of regions, then because of like how we draw the regions, it's always going to give you a planar graph. There's not ever going to be like any crossing of edges if you're going to like be constructing a graph like from a map like this. It just doesn't happen. So you take a map like that, you translate it to a graph. That graph is going to be planar, and then the theorem here says that that planar graph must be colorable with no more than 4 different colors. And you know, maybe you can color it with 3 different colors, like in this example, or maybe even 2 colors, or you know, if it's just a single region, technically you could color it with 1, but like no more than 4. And so that's a pretty big theorem, and it's pretty hard to justify it, honestly. Okay. Oh yeah, I should have just copied and pasted from here. Yeah. Okay. So here is that that connected graph, the star and the hexagon thing that I was talking about. So how many colors are needed to color the following graph? So we're just going to color the vertices. So there are 1, 2, 3, 4, 5 vertices, and if you remember how this thing is defined, like these things right here in the middle, they're not vertices, they're just crossings of the edges. So like our only vertices are like these 5 points of the star, nothing else. Okay, so if we wanted to color these, so let's make that top vertex be blue. It's connected to this one, so these two have to be different colors. And then this is connected to this one, so those two have to be different colors. But this is also connected to that, so it can't be red, right? So it has to be green. Okay, and then what about this one? So this one's connected to blue, so it can't be blue. Oh, it's also connected to red, so it can't be red. Oh, it's also connected to green, so it can't be green, so let's make it purple. Okay, so we have to use 4 colors at this point. Can we do it with just 4? Like, all right, so we have this last one, and this one is connected to blue, can't be blue. It's connected to red, can't be red. It's connected to green, can't be green. It's connected to purple, so it can't be purple. So it has to be just something else. So let's do orange for funsies. So yeah, it seems like we actually have to use five different colors here. And this does not contradict this theorem at all, because this theorem only applies to planar graphs, which I just kind of waved my hands at saying, like, this is not a planar graph at all. Maybe I can draw the picture now of like what I was kind of talking about earlier with like the... Do that, get rid of that. Okay, yeah, so what I was saying earlier, like you could like take this this edge and just kind of scoot it outside like so. So just change this one to that. And then you could do like a similar thing with like this edge right here. So let's scoot that one outside. I'll do the snappy thing. Yeah, snappy thing. Okay, so we scooted that one outside. And then we have these two in here are still crossing. So we just have to remove like one more crossing. But this one, okay, let me do the scooty thing. Okay, do that. No. No. All right, one more time. There we go. Okay, cool. Okay, so like no matter how I like take this thing and like drag it out here, if I drag it out here, now it's crossing over this one at this point right here. If I drag it like, you know, over here, this is like terrible. If I keep it inside, it's crossing this one. If I take it outside, it's crossing that one. So no matter what I do with it, it's just always going to be crossing. Okay, should have done that earlier. Oh well. So anyway, so I've been hinting at this thing called chromatic number for a while now, and the chromatic number is just the minimum number of colors needed to color a graph, so that, you know, the whole condition that we've been discussing the entire video. No edge connects vertices of the same color. So any two vertices that are connected by edge have to be colored different color. So the minimum number of colors that you need to color a graph, and the way that we've been doing all this video, is called the chromatic number of the graph. So so like this theorem basically says that any planar graph, the chromatic number cannot be any bigger than 4. Maybe it's 3, maybe it's 2, maybe it's even 1 if it's just like a single vertex. But it can't be bigger than 4. That's what this is saying, that the chromatic number cannot be bigger than 4. This slide, we basically proved that, well, I guess we didn't prove, but like we kind of convinced ourselves that the chromatic number of this complete graph on 5 vertices, that this chromatic number was equal to 5. Okay, so the chromatic number of that thing was 5, and it wasn't planar, so that didn't contradict the theorem or anything like that, so on and so on. So we've talked about like 4 colorings. We haven't talked too much about 2 colorings. So I'll say there's not like a good way of like saying like what the chromatic number is for most numbers. Like there's no good way of like saying, yes, this is when the chromatic number is equal to 7 or equal to 3. There's not a lot of like good theorems like that out there, but there is one for 2. So this theorem right here says that a graph is 2 colorable if and only if it has no circuits that consist of an odd number of vertices. So for example, in this graph right here, this does have a circuit of an odd number of vertices. So this circuit right here has 3 vertices. So this is not 2 colorable. This graph on the right, this, so let's see, let's take a circuit. So it does have a circuit with 4 vertices. What if I start right here? That's also 4. No matter where I start, any circuit that I do is going to have an even number of vertices. And so this over here, according to this theorem, would be two colorable, whereas this graph on the left would not. And we can kind of understand this a little bit better too. So like it should kind of make sense. So if I were to make this be blue, then this one would be red. And then in this circuit, so we're just looking at this like odd circuit right here. So this is blue, this is red. And then because this is an odd circuit, we get to this point right here where like, you know, we could like kind of keep alternating. But at this point we have to, like, because it's attached to the red and it's attached to the blue, it has to be like a different color. But if you have an even cycle, well, in that case, you could just do alternating colors. So blue, then red, then blue, then red. And because there's an even number, it just alternates an even number of times. But if it's alternating an odd number of times, then so you do blue, you do red over here, and blue, and then this like odd vertex at the end is going to be touching a blue and a red, so it has to be something else. Okay, so that's useful. So here's an example. So I recommend pausing the video here and seeing if you can determine whether the following graph is two colorable. Okay, so I'll give you a couple seconds. Pause the video, see if you could decide for yourself. Okay, so there's two ways you could do it. You could just go ahead and try to color everything and see if it works out, or you could just kind of count like cycles and stuff like that. So personally, what I would do here is actually just try to color it. I think that would probably be a little bit easier. So I'll just make this one blue, and then anything it's touching, I'll make it red. Anything the anything the reds are touching, excuse me, the reds are touching, make those blue, and then anything those blues are touching, make that red. And now check to see that this is a valid coloring. Okay, so blue touching only reds, blue touching only reds, blue touching only reds, and then same for the reds. This is actually a special type of graph called a bipartite graph, where you have you kind of split it into like two groups of vertices, everything on the top and everything on the bottom. Everything on the top, like, they're not touching each other at all. They're only touching things on the bottom. And then everything on the bottom, same thing. There's no edges connecting like the vertices on the bottom to each other. There's only edges connecting the vertices on the bottom to the vertices on the top. So this is actually like a special thing. Anytime that you see a bipartite graph like this, it's going to be two colorable. You just make all the top ones blue, all the bottom ones red. It just works out. Here's another example. Determine if this graph is two colorable or not. Again, I'll give you a chance to pause the video and determine for yourself. Okay, so you could go ahead and do the same thing of just trying to color the vertices, you know, blue, red, red, blue, and then we start seeing a problem in this top right thing over here, because you know, this one would have to be green, because, well, now we can actually apply our theorem like, oh, well, if there's, you know, it seems like there should be an issue, then if we want to justify the fact that it's not two colorable, we can just easily apply that theorem just by saying, hey, this is right here, this is a cycle with three vertices, so this is an odd cycle right here. So we have an odd cycle, and so therefore it is not two colorable. Therefore, its chromatic number has to be bigger than 2, and we can now conclude actually the chromatic number of this graph is equal to 3, because we proved that it's not 2 colorable, and then we demonstrated it has a 3 coloring. All right, so we're going to end with an application. So let's suppose that we are trying to schedule times for clubs to meet in a way that all students can make it. So how many time slots are going to be needed? So here we have a table, and in this table we say that, well, Harian here, she is in the fashion club and she's also in the book club. Liu Kang, he is in the extraterrestrial and the book club. Akshat, Mita, so on and so forth. Okay, so if we need to know how many time slots are needed, what can we do? So, so let's say that like volleyball, let's say that volleyball and fashion decide to meet at the same time. So if volleyball and fashion decided to meet at the same time, this would be a problem because Mita is in both of those clubs. Okay, and so there would be a conflict created there, and so it's just not going to work. Okay. Similarly, like, if the fashion club and the extraterrestrial club decided to meet at the same time, actually this one would be fine because like Harian and Mita are in the fashion club, but neither of them are in the extraterrestrial club. And then same for Liu Kang and Akshat with the, vice versa. Okay, but if we were to look at the book club and the extraterrestrial club, if they were to meet at the same time, then Liu Kang would not be able to make it to both. Okay, so here's what we can do. You could just trial and error this whole thing, right? Or what you could do, and this will like be much more useful for like bigger and more complicated examples like this. I'm just going to do like this simpler one just for the sake of just demonstration. What you could do is translate this information to a graph. Okay, so we're going to have 4 vertices, and each vertex, so what is going to be our vertices here? You kind of have to think about it. So like, are our vertices going to be the people, or are the vertices going to be the clubs? And you're usually just going to have to kind of like reason your way through this. Okay, so we're gonna make the vertices be the clubs. So we'll have volleyball, we'll have fashion, we'll have extraterrestrial, and we'll have book club. Okay, so if and then what are the edges going to be? The edges are going to happen if like 2 clubs have someone that is in the that is in both clubs. Okay, so for example, let's see. Volleyball and fashion. Is there an edge between volleyball and fashion? Well, yeah, because Mita is in both of those clubs. So we'll draw an edge from volleyball to fashion. Okay. What about fashion and extraterrestrial club? So fashion and extraterrestrial club, like we were saying earlier, they don't have any overlap between members. So there's not going to be an edge between those. Okay. What about volleyball and extraterrestrial? All right, well, Akshat's in both of those, so there will be an edge between them. And what about volleyball and book club? Well, there's no overlap there, so can ignore that. All right, fashion and extraterrestrial. Or already did. Sorry, we already did that one. Let's see, we did volleyball and fashion, volleyball and extraterrestrial, and then volleyball and book club. All right, so we're done with all those. Volleyball and extraterrestrial, we're done with that one because there's no overlap. Fashion and book club, Harian's in both of those. So we put an edge there. And then extraterrestrial and book club, Liu Kang is in both of those. So We make that. Okay. So in this graph, what we can do, we can just, I probably should have done this all in black just because we're going to color everything. So we can color vertices. So each color is going to correspond to a time slot. So blue can correspond to like 1 p.m. or something. And red can correspond to 2 p.m. and green can correspond to 3 p.m. and so on. And we want to use as few time slots as we can. So in this example, we've translated this to the graph, and so we can just color this graph. Boop, 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 boop. And we just need to make sure that like any two clubs that share an edge have different colors. And what does that mean in the context of this problem? Well, okay, so volleyball and extraterrestrial club, there's an edge between them, meaning that like there's a conflict there. So they have to have different time slots. So they have to have different colors because the color is the time slot. Okay, so if there is an edge between them, then that literally just means that that they have to like pick different times because they have someone that's in the same that is in the same club, right? So it's okay that volleyball and book club are meeting at the same time because they don't have any overlap, and then same for the fashion and extraterrestrial club, but because the volleyball club and the extraterrestrial club, they have some overlap, same with volleyball and fashion with Mita, then they actually have to be at different times. Okay, so you can just take some information like this, you translate it to a graph. You kind of have to sometimes think a little bit like, okay, do I want the graph to be like the vertices are these things, or are the vertices going to be the students? But then you just kind of make sense of it, like in terms of the problem, and then convert that to a coloring problem, and the coloring problem will typically be easier to sort of handle. Okay, so I think that's it for this video. Thank you for listening, and I will see you in the next one.